तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have been looking into the organization of our code, Verilog code, and we had covered a non-retrievable monoshot in a sequential circuit. And today we will continue from this, and we will go on to see how a shift register is implemented. And so this has been explained earlier, and we will have a look once again. And the code for this is here, and as usual this is the comment field, line comment, and we have an assign statement which produces a combinational output as such. And here what we want to do is write shift by 1 bit, and what we are doing is we use a symbol like this, and 2 greater than symbol. It implies it is a shift, and that is right shift, since you can regard this as an arrow pointing to the right. And how many bits you want to shift can be indicated here. And if you want a left shift, you just invert this to the mirror reflection of this. And we assign this shifted value onto this. Say it goes by the same name with an extension called next here, implying thereby that we are pre-computing this shifting so as to register it when the event happens. The event is positive edge of the clock, and here also we have based upon the reset, we initialize or rather preset the desired value here for the shift register. And in hexadecimal you can regard it as all AAs. So it's a normal convention for designers to use AA and 5 for bit test as such. And if a shift is encountered, this is a one-time affair at the time of power on condition, and normal working is we look for a shift to go high, and if that happens, only then whatever was shifted earlier using that next, we assign it here at this point. That means to say this will be assigned, transferred to data out 1 only at the positive edge of the clock. Otherwise don't disturb. This is the usual thing that we have already seen. And the same shift register can also be implemented in this fashion. It is exactly the same, except that the assign statement is slightly different, in which case what is our goal? It is to write shift by 1 bit. So what we can take those 15 to 0 bit. If you write shift, what will happen? 0 bit will get lost. So what remains is 15:1. So we just concatenate two numbers, that is 0 on the MSB, because vacated bit will always be 0. That is the nomenclature adopted earlier for that arrow that you have seen there. So this does precisely the same thing as that one, and it has been named 2 just to distinguish from that. When we simulate, we can easily compare the two and say that see that it is basically the same. And this is the concatenation of 0 for the MSB, that's a bit vacated, and shifted is on the right here. So 15 bits here plus 1 bit here. So total it makes 16 bits. That is precisely what is here. And once again, as in the previous case, this is precisely the same as the data 1 case. So I will not go into the details. Again, preset here, and then shifted contents are moved into that. And this is not to disturb if any other condition occurs here. And next we had taken was parallel to serial converter, and this is what we had in parallel to serial converter. We have a power on reset or system reset, and whatever value that you want to serialize, you have a parallel information that can be entered into a shift register inside in this box, and through a 16-bit data bus. So if whatever data you want to send out, serialize and send it out, you can load through this, and provided you assert a load input as such. And once you have loaded, then you can you have one more control called shift control, because together with that you have a right or left shift available. It's basically it's a shift register. That's why we use this. And all this shifting will happen only at the positive edge of the clock. And out comes single bit data, because that's what we want, parallel to serial. This is the parallel information, and we want to serialize, and every clock pulse you at the positive rising edge of the clock, you get a data out. When the data is valid, is indicated by another signal called data valid, and when all the 16 bits have been converted, thus on the end of conversion is asserted here. And as far as right and left shift is concerned, right is active high and left is low as such. That's what is mentioned here in this. And looking at the code, we had one always block here, because we want to take action at the positive edge of the clock, and as usual we have a system reset here, which resets all the registers that we have. The registers are data out and data valid and end of conversion, which is same as the output here. After resetting it, we look for loading condition. When it is asserted, what we do is, as I said, internally it has a shift register, a nomenclature as SR, and it is 16-bit in width. And this is the input actually. Here what we have seen is this is the input. Whatever is at the input is assigned to the shift register. It's just copied inside at positive edge of the clock, provided load is 1. That's what we want. And we also have a counter inside. Here that counter is preset to 16. This keeps track of the number of bits that has been sent out. Say you want to send 16 bits of information. That's the reason why it is 16 here. And data out and these things are not to be active asset. So we just retain it as 0. Here we have we want to shift only if this signal goes high, and also we should have that counter non-zero, indicating some more bits are waiting for transmission. So, but if it becomes 0, we stop the transmission, and for this condition we naturally have to do the shifting and output the result as such. So this is basically a mux to do that job based upon right or left signal. Right means 1 here. If this signal is 1, then we do the right shift using the conventional statement, and then assign this one back to itself here. So it is overwriting itself, and then there is one more possibility here. If it is 0, you left shift here. That's what we want here. Whether we want a left shift or right shift is merely governed by this, and that's what is being done here. Right shift is done here, left shift is done here, and that shifted results will be transferred to once again back to the shift register here. This is for actually registering as such. You want to what we have seen is a shift register used internally that doesn't come out as such. So the output you had to route that one to the actual data out, and that's what we do once again based upon the right or left shift here. If it is right shift, what we had to do is we had to assign SR0, because when you right shift, LSB will be sent out first. So that's what is being done here, and that is being sent to data out. Mind you, data out is only a single bit output as such. And on the other hand, if it were left shift, that is this will be deasserted, that is logic 0 low, and then in this case we have to send MSB out. That's what is being done here. And having done this, you had to decrement the counter that we had, which will keep track of the number of bits sent. Earlier it started with 16, now it will decremented it to 15. And now we have started outputting the data. Therefore, data valid is also asserted here, and end of conversion is deasserted because it's not a time for it. And on the other hand, if this condition is satisfied, that is when it has output all the 16 bits. So each time it will go only through this path as such, and it keeps on outputting bit after bit after shifting. And when it touches 1 here, even then it will do, because one more bit is to be processed. Next time it comes over there to this condition will not be satisfied. Similar condition was there which was non-zero there, and that condition will not be satisfied, therefore it won't reach this, and instead it will come to this and process from here. So which says so long as shift is still asserted and the counter is 0, signifying that all the bits have been already sent, then we take this action. So in this case we have finished the job. In fact, the previous positive edge of the clock itself we have completed the job. Now in this edge we need to just deassert the data valid, because we are not outputting any data as such. That is what is here. The data is 0 here, and naturally end of conversion is over, therefore we assert here. And if no other conditions are satisfied, nothing is to be done here. That's why no statement has been put, and just a semicolon put. And we started with an always block, so there was a begin and its matching end here. We also saw a model for a state machine, that is what is here, and you have Z0 to Z3 states, and these are all the outputs. For example, this is only a simple output to indicate in which state you are in, either in S0 state or S1 and so on. And based upon two inputs, in 1 and in 2, you can make the transition from one state to another. So for example, so long as this in is 0, so you continue to be in the same state. If it is 1, you go to S2 state and so on. So this we have already seen, and we'll look at the code as such. So once again, when reset is encountered, we clear all the outputs here in this case, and initialize it to S0 state, note that I have made it 0. You could have made even 1 as such, because that's what the starting state is, S0 state. But anyway, this will automatically take care, and because with the next arrival of the next pulse, it will go into S0 state, in which case we would have already covered that. So there's a case statement here, and in order to go to different states and process whatever is required for that particular state as such, as per the state diagram that we have already seen, and that's based upon the state here, and this has been defined as using a define statement, and here in this state we need to switch on Z0 here and switch off all other outputs here. And suppose in is 0, then what we need to do is remain in the same state. That is what is here. So remain in the same state so long as this is 0. If in is 1, it has to go to S2 state. That's what is happening here. So, we compared in 1. If it is 0, you go to if it is not 0, then only it will go to this statement. That's what we want. If input is active, then go to state S2. And in this case, Z2 must be set, all others reset. And we are in S2 state. So let us see what to do beyond this. If int2 is 0, we need to go to S1 state. We are in S2 state right now. It's here, and we had to, if int2 is 0, we have to go to S1 state. That's what is here. That's what state is therefore assigned to S1 here. If not, that is int2 is 1, we need to go to S3 state. And similarly in S1 state, it all depends upon the inputs. It may come to this state only when those conditions are satisfied. Suppose it has come to this state, then you need to switch off all except for 1, that is here. And once again see into condition, and if into is 0, go to S0 state. So we are in this one. If into is 0, take to S0 state. Otherwise, that is into equal to 1, you remain here. For 0, 1 you remain here, and for 1, 1 you remain in this. And inputs will take you to either this state or this state, depending upon these two being 1. So this, note that this and this are same precisely, and this state is same. And that's what is here. Into is 0, it takes you to the initial state. Otherwise, that is once again we check in 1 also, because two conditions are there. If it is 1, here it will make an entry only with the into equal to 1, because if it were 0, it would have gone there, right? So here at this point, into is 1. That means both are 1 here. So automatically it has to be taken to state 3. That's what is being done here. If not, that is into is 1 and in 1 is 0. So 1, 0 must take you to I'm sorry, 0, 1 must take you to this S1 state. That's what is done here. So otherwise you may encounter next state. So it's similarly processed for S3 state. Once again that LED is on, and once again you look for the into input, and based on that you go either to S0 or S1. If both conditions are not satisfied, go to S3. That's what we have here. So, right, if into were 0, it went to S0, and if it were same 1, 1, it remained as such, and when it became 0 1 it went to S1. That's what we have already seen. So S1 and then S3. So we also put a default state to take care of tri-state or don't cares occurring in this. And then we started with a case and therefore an end case, and on begin matching end is also there. So next we had considered was a pattern sequence director, and this directed 0110 sequence, and for example we may consider one of the input patterns in this fashion, and wherever the very first occurrence 0110 happens here. So right at that last 0 the output must be 1 there, and once again 0110 is occurring here and corresponding 1 is available here, and once again 0110 one more 1 here. This is what we have already seen. And this being a sequential circuit, we once again use an always block with positive edge clock, and as usual we have a reset, and we reset, we have only one input and one output as such, because this sequence director as such. So we initialize the output to 0 whenever a reset condition is encountered, and we also make the state 0 here. This will deal separately the state. Earlier example we had used the actual name itself. We called it by name, say S0, S1, etc. for states. Now we can let us call it by a decimal number, which is easy to deal with. And this one is as per this diagram. So here this implies in the first one is input, and the output is the next one, right? And the conditional outputs basically. And we have 4 states here, S0, S1, S2, S3, and we'll deal with straight away a decimal number instead of a binary number, although binary is put here. And so long as 1 is input, then we need to stay in the same state, and if it is 0 we need to go to 0 1 state, and in both cases outputs are 0. So that is in case 0. So we are having a decimal number instead of name S0, S1, etc. right? And output needs to be 0. That's what we have seen. And once again we use a mux for this state for determining the next state as such. It all depends upon the in. If it is 1, we need to remain in the same state. That's what we have seen in the figure, and otherwise we wish to go to S1 state. In when we come to this 1 state, so we'll just we still need to output only 0 because that 0110 pattern has not yet come, and state will have to be either 2 or 1 depending upon in equal to 1 or 0. So here if it is 1 it has to go to S2, and if it is 0 remain there, and the outputs once again are 0 here. And in this state you can go back to S1 state provided input is 0, and output corresponding to that will be 0 here. So in S2 state input is 0, should take you to S1 state. Output is 0, right? If input is 1, it should 0, it should take you to 1 state, right? Otherwise it should take you to state 3. We are here, so state 1, or it should take to state 3, and here also the output is 0 here. That's what is here. Then in the third state, if in is 1, then you need to go to 0 from the third state, and otherwise 1, right? Just remember, 0 or 1 depending upon n equal to 1 or 0. That is as far as the output is concerned. Here, as far as the output is concerned, this is 1 here, right? Otherwise it is 0 here, depending upon the condition whether input is 1. For input equal to 1, it should go to it should output 0, whereas it should output 1 otherwise. That's what we saw here. And looking at the state here, we are in S3. So if input is 1, it should take you to S0 state, and otherwise it should take to S1. So just remember S0 and S1 for input equal to 1 and 0. Input equal to 1, so it takes you to 0, and for 0 it takes you to 1. And state also depends once again on input, and if it is 1, it should take you to 0, otherwise 1 state, right? So n equal to 1, it should take you to 0. Here input is 1, so it should take you to 0, otherwise it should take you to S1. That's what we have seen in that. Here. And a default condition is also accounted for, so which takes you to a safe 0 state as such. And this is a matching end case that we have here, and an end also. And this will be the end of the sequential circuit design as such. We have written combination as well as sequential circuit as such, and the question is how do we test them. So we need to write another Verilog code as such called the test bench, and it also goes by the name stimulus, and we'll stick on to this nomenclature of calling it a test bench as such. And so notice that what we are going to write is a test bench, and this is actually a file, and as I mentioned earlier, we try to retain the very same name for the file. See, this one is a test bench for combination circuits as such, so I give the same name here with an extension of test, signifying that this is a test bench. Some people are in the habit of giving TB, that's also alright, right? Whatever the designer is familiar with, he can adopt that. And this is a .v file once again, signifying it is a Verilog file. We'll see how to write a test bench, and prior to that, let us understand what a test bench is a little more elaborately. See, we have a design module. So what we have already seen is a combination circuit, which is a design module, and similarly another design module called sequential circuits. So we are, if you take a combination circuit, your design module will be the combination circuits, right? And that is the file that you have to test, and that is the actual, that's called the design, and the code which will test the design is called the test bench, and that is what is in this present file as such. And you need to apply stimulus. Stimulus is nothing but application of different inputs at various points of time, and that's what we are going to do in this particular exercise as such. And we apply a stimulus and look for the results, and we had to you are the designer, so you know how a circuit functions, so you can always cross check whether it is functioning as per your requirement. So that's how you have to do. So that's what this says. Once the design is completed, functionality must be tested. That's what we have already seen. And how to test is to apply stimulus from the test bench and then onto the design module as such, and then check the results. How we check the results we'll be covering in simulation later on. And right now we will concentrate on how to write a test bench.
Like this stimulus file, can I write a file that will check the results by itself also?
Yes, you can display that, but once you start using simulator, and that will be your method will be a very painful thing. So we use a timing diagram as such. It will be very convenient, and you can quickly look into that, and analysis will be faster. And that's why it's generally preferred, especially with designers. That is very popular. That has also picked up in institutions, just as it is popular with in industries. And first thing we had to, this is the very first statement in the test bench. What we are doing here is, we had a design called combination circuits, and that particular thing was a different file. It is not this file. This file is combination circuits _ test. So it should be very clear. That's why earlier we put a block separating out the test bench and the design. But how does this know unless you mention? So this is the statement that you have to give in order to identify that there is a design called combination circuits, and that is external to this present file as such. And so in order to do that one, you say include. This is very same thing as a C command instruction, right? We have a tick here, a reverse tick here. This is a must here. This is a keyword that you cannot ignore, and separate with one or more blanks or tabs, and then put within quotes. These quotes are also required, and then it is note that it is an .v. So you have to completely specify the file name. If you want, if it is in some other directory other than this present thing, you have to give the entire path as such. And but it's a good practice for you to keep everything in the same directory as such. And in which case you don't have to put that. So we have another. We are going to simulate your code, right? So we are what we are going to do here is stimulate it. That is to apply different pulses with reference to different times. So there must be some time base to tell the system that you want a time base of say 1 nanosecond. So in that case you have another statement. Once again a tick and a time scale. A space must be given. Then say 1 nanosecond, or you want 1 microsecond, 1 US you can put here. And you want how much resolution you want, that also can be specified here. For example, it is a 0.1 nanosecond resolution here. 100 picosecond means 100 by 1000. So it's a 0.1 nanosecond as such. And that's what is put here with a resolution of 0.1 nanosecond. So next thing is, as we had done for the design file, we need to declare the module. So the module actually starts here. These are all extraneous things to the module, in the sense that this is defining the time, and the earlier thing defined which is the input file, design file. So this is outside this module as such. So the test bench is the module. This is the file name, and it's a good practice to retain the very same name as you have the module name, right? There is no compulsion that you should have same. In fact, I mentioned that you had to have, but it's cross-checked. It's not. You can change the name, but readability will be easier if you are maintaining so many files. If you have the same file, you can easily spot it out, and that's why I prefer this. Retain the very same name here. So here you declare module and with a space, and then the actual module name you give here. And this happens to be the test bench, so you give the full thing. And notice that .v is not to be given here. If you give .v, I think compiler will complain, right? And notice that in design we had listing of IOs, and here we are. This is only a test bench, so there is no other higher module for this. So that's why there are no IOs here. So we dispense with that brackets as well, and with listing of the IOs, because there are no IOs for the test bench here. And whatever are the IOs in the design module, that itself can be viewed right from this top. This is the top of the design actually. Actually, when you say design, when you refer to the top module, you refer to the actual design module as such as top. But in this case, when you test and have a test bench, the test bench becomes even higher level than the design module, because the design is being called by this test bench as such, and that's why we don't have IOs, and therefore we have not listed that. And don't forget the semicolon, which tells the module has at least module definition has ended, not the module has ended. So in order to communicate that module has ended, you have to have an end module which will appear at the fag end of this code. And here now the difference is, in design file we said input etc. we had declared, because that was appearing right here and we were listing, and therefore you won't find any inputs and outputs listed separately here. Instead you have reg and wire here, and we'll explain why a reg and why a wire. And for example, in the design you have had all these as inputs, say A, B, C, then I naught and so on, right? For example, these are all general inputs that we have had for A, B, C, and here what we are doing in test bench is we declare it as reg. Wherever inputs are concerned, it is a reg. You should not confuse with the register that we have had using always and positive edge clock earlier for implementing flip-flops, right? That reg is a totally different thing from this reg. What all this means here is, we want to hold this value because what we are going to do is test our system, and testing implies we are going to go from one point of time to another. So we may be right now at the 0 time, and we'll move on to say next 10 nanosecond and 20 nanosecond and so on. So we may go step by step advance in terms of time as such. So when we do that one, unless this is held firmly, you won't get a stable input as such for your simulation. Therefore it is essential that you declare it as reg, and if you declare it as any other thing, it may tool will complain again. And here these are all general inputs we have had for the combinational circuit as such, and we remember that we had an 8 input mux, that is I0 through I7 are those inputs for this mux. In fact, we can have a look. This is what we had, right? And then we had a magnitude comparator. It contained N1 and N2 as two 8-bit numbers as such, and that's what is here. Say N1 and N2, it's a magnitude comparator, and
everything is a register.
I didn't get you. Everything in sense? All inputs. Yes, they are all inputs are registered because you want to hold this value. You can change only when the time changes. How to change the time we'll see shortly in this. And once again we have a multi-bit representation. This we have already seen earlier, and we also had another design example in which case we just summed two numbers, num1 and num2, and each of them are 8 bits as such, and once again these are all inputs, therefore reg has been declared here. And there was also a preset value which was compared with the sum of these numbers, and when a match was found, we reported that. That's what is the example here, that is this here. That's the one, right? We had two numbers here, we added this one, provided enabled sum is energized, and only then the sum will be non-zero, the actual sum actual. And when the sum equals preset value here, this I have just abbreviated because there is no space to put here, and when if it is equal or greater or less, then you get a match more or less as the output for this design example as such. And that preset value is 9 bits as such. That's what here. And then as far as the outputs are concerned, this is basically combinational circuit outputs. So using either always block or assign statement. And here we had to declare it as wire. So why it is a wire we'll see little later on. Right, I'll explain why it is so. And we had F1 through F12 earlier for buffer, inverter, etc. That's what I don't have to show it, I suppose, here. And all of them are outputs. So it's declared as wire. We'll come shortly to that. And we had some other outputs, which is 3 bits in width, and therefore it is mentioned as 2 to 0 here. And all the outputs or combinational outputs are all wire. So it is very simple. In test bench, all the inputs are declared as reg, all outputs are declared as wire. Right? It is note the difference between a design file and this. And we also had full adder as such. One was behavioral statement we have had, and that is here. And that corresponding output sum is these are 2 bits as such. The first bit signifies it is sum, and carry is 1, right? And this is a behavioral thing. And we also covered a data flow here, and that is differently named, right? So as not to overwrite when we simulate. And corresponding carry out is also here. And we also had a gate level implementation of the same, and that is here, sum and carry.
You said why a wire is output is termed as wire.
Pardon?
Why an output is termed as wire?
Yeah. No, I'm yet to say that. Right? When we touch on the instantiation shortly, we will see that. So we also had a magnitude comparator, and those outputs are F3 to F18 here, and that's as per this. This is the one, F13 to F18, for various conditions which we have already seen. I don't have to go into this, based upon 2 numbers N1 and N2. And we also had summing, which we have already seen there. So that was the previous slide we have seen. And corresponding outputs, we have seen input there. Now we list the outputs here. And now coming to that explanation of wire, before that we will see how to instantiate a design module. We are now right on the test bench, and we are yet to call, we have identified IOs rather of the design module. But how are we to press the design module into service? So that is the question. How to call it? So the way to call it is just name that. Here in this case the design module is combination circuits, underscore circuits, not the underscore test. Underscore test is this test bench which we are right now on, right? We are going to call this one. So when we call, what it means is when you convert this into an actual working circuit as an IC chip as such, then what happens is this circuit will actually function because of this statement, right? So you have to what is called instantiate here. So whatever is the design module, you have to call that module. That is known as instantiation here, and you just put that particular design module name. That's all. Are you clear about it? So this is different from the test bench. We had declared a module called the combination circuits underscore test, but whereas we are calling the actual design only here, and this you can call any number of times. So it is similar to, suppose you have circuit diagram, let us say we have a TTL gates, say 74LS00 you have used. There are 10 numbers on a board, and how do you identify? You identify them as U1, U2, U3 and so on. That is the nomenclature you adopt. And same is the case, very same thing has been adopted here also. You can just call this once and then say you treat this as one particular package, one IC. Like this you can call any number any times, right? And any other module you can call here. So now once you call this one, and there are IOs here, we have to list these IOs, and those IOs, how do you express them? We'll see, that also is a new thing we have to see here. And before that, let us see why that wire is. Why should we declare that output as a wire, right? See, I pointed out that like this we can have a number of modules in the same test bench, or even within a design you can call any other design, sub modules you can call. So in which case there must be a way to identify the connection between one module and the other. So how do you identify? So it is nothing but, if you look at the circuit as such, which you have hooked up earlier days, you physically connect one particular pin to another. It may be from one IC terminating on another IC. So the connection is nothing but a net, or simply call a wire. So it's a physical wire there. So here we want to connect one, it's equivalent to connecting one IC with another. This is U1. You may have another U10. You want to connect a particular pin to U10 from this some other pin. So you want to you have to declare that as a net or a wire. That is the funda there in declaring all the outputs here as a wire. Are you clear?
The output is defined as wire. The next chip's input will be reg only, right?
No, that would depend upon whether it is within a design or in the test bench. If it is in the test bench, that is right. If it is design, that's not correct, right? Depending upon the actual circumstance, you'll have to do that. You are right as far as if it is test bench, right? And now we have one more new thing introduced here. This comment is simply that we are instantiating. This is called the instantiation, followed by the IC, so to say an IC number, identification number, and then you list as usual with the opening bracket here, and there will be an end bracket here, and you list all the IOs. So because this is a design module. Now as I said, you have a pretty long list here of IOs, right? So what is the guarantee that you have adopted the very same format? For example, if you had put A here, and inside this actual design what you have put earlier, what is the guarantee you have put in the very same order? Suppose you violate the order, right? So the whole thing will become a mess. So suppose you put A there and C next there in your design module, and without this dot A convention, if you had just used just A, and you had for the next you use here B, whereas in the actual design module it is C. So there is a difference between the design module and the present module. So if there is a difference, then it will report error, right?
Order matter here, you're just defining.
See, order matters because you don't know whether it is an input or an output. As I said, you can have a free mix of input and outputs, right? Unless you maintain the very same order, how will the tool know? You can have very many combinations. You can put one thing there and totally radically change from that combination. How does the tool know? It doesn't have that much intelligence. You have to inject that intelligence, right? So the way to do this is what is called connect ports by name, right? Okay. So how you connect the name is you use a dot here, and these two need not be the same. This means within brackets you are implying these signals are, the A signal is within this test bench. Are you very clear about this? This what is covered within brackets is within the test bench, not in the design. Whereas this means this is the nomenclature adopted in the design. So that's how you tie between the various permutation combinations. For example, I can just remove this and paste somewhere here at random. Still it will work. In any combination you can put. You can have a twisted jumble of such variables. It will take care for simple reason you are saying which is the current signal for the test bench, which is the signal for the design. You are discriminating. So, to repeat again, this one pertains to this test bench signal, whereas this pertains to the actual design. So dot A means this parent. So the parent or the other way you can call, right? What this implies, it is design. So that is the nomenclature. So what all we do here is just list all the inputs that we have already seen, right? in the same fashion. By doing so, you can, even if you swap the order by mistake, right, it will automatically take care. That is the purpose there. And all good designers adopt this scheme. So I highly recommend that you also adopt the very same thing. And these are all we have already seen pertaining to where inputs and outputs are. All are listed here right up to this. This is for the demux case here, and these are all the outputs that you have here.
In the bracket you can give different names.
Yeah, with a different name. It need not be the same name, right? This pertains to the present one, right? I can give it as F25. That's only so long as but that will have to be declared as a wire here in this particular whatever level, whether it is a test bench or even in design module you declare as a wire, which we'll see when we deal with bigger applications, design applications. When we take that, we'll see how to make compact modules, and whereas we have put here as a segregated thing, this appears to be little out of place. But the point is, I have just I wanted to show in one platform as far as the simulation and synthesis tool is concerned. That's why it has been clubbed, although some of them may be a disjointed thing. It is to have it's some sort of a ready reckoner that we have if you combine all this. Otherwise, we could have had a small modules which we'll be taking in the future, and that's how it has to be designed. We'll see consider depth later on when we come to that. And this exhausts the first module name, and I think I'll stop here and continue later on in the next class, and we'll see how to get how to mention the time and so on, right? We have one more test bench for sequential circuit also. That also will be covered in the next session. Thank you.